Greetings. My name is Michael Race. I'm a principal R&D engineer at Visimix Limited, and I'm going to show you some features and nice characteristics of Visimix Turbulent, which is a product of the Visimix suite. For the beginning, let me share my screen with you, and I'll show you a little demonstration of how Visimix Turbulent works. Let's create a new project. Let's name it demo. And let's select for our first project, insulated tank without jacket and with elliptical bottom. Now we have to enter major geometry parameters of the tank, which are inside diameter, total tank height. The system calculates the volume. Now we enter level of media, and the system calculates volume of media. And when we are done with the tank, we move to baffles, and let's choose configuration without baffles for the starter. Let's now choose impeller, pitched pedal impeller with some reasonably selected parameters. Follow me, please. It's very straightforward. We enter here 80 and something reasonable here, 200 RPM and 6 kilowatts. Now we have to enter density of media. Let's assume that we work with water, so it's 1000, and dynamic viscosity was 170 plus. And with this set, we are ready to submit the first request to the software. Let's calculate main turbulence characteristics. Vortex reaches impeller. Gas insertion from surface and shallow vibration are possible. After we have this warning message, everything else is unreliable, but let's take a look, and we see some characteristics which probably don't have much physical meaning. In order to do something, we first of all have to enter baffles. And as soon as we enter some reasonable dimensions of the baffles, we will try again. Now we have another kind of message that the mixing power is too high for my drive. Okay, let's try to do something with the RPM. Maybe we will reduce RPM to 1600, and it would help us. Now we are okay with the results, and let's do something different. Let's try to calculate liquid-liquid mixing. Let's do kinetics of drop breakup. And now we have to enter again the physical parameters of continuous phase, density, viscosity, volume fraction of dispersed phase, its density, and its viscosity. Now let's do 0.03 for interface facial surface tension and 0 for index of repulsing pressure using this hint. We have some warning message that the actual density and viscosity of multi-phase system, liquid-liquid system, is different than the originally entered data for single-phase system. And let's ignore it because the data are pretty close, and try to find out what do we have with kinetics of drop breakup. It starts with about 800 microns and quickly goes down to about 400 microns. Wonderful. So I think we're in a good shape. In order to finish working with this project, let's ask another question about mean drop size. And the mean drop size is about 400 microns. Now, let's assume that we are not very happy with this dimension of drops, and let's try to do something with the impeller again. In order to do it, let's create a clone for our project, and for this clone, we will update the impeller. Right now, we are choosing impeller, and instead of pitched pedal, let's choose pedal, and let's stick with the same tip diameter, with the same number of blades, but let's use a much wider blade. Let's lift it up from the bottom a bit and reduce rotational speed to 70 RPM. Let's stick with 6 kilowatts of motor power. Now, let's do, first of all, main turbulence, and we have some other data. And right now, let's calculate liquid mixing and mean drop size. The same warning passage, we ignore it, and now we have the mean drop size. Let's close the windows of drawings which we do not need for our subsequent work, and try to rearrange everything that we got so far. On the left, we have our new project with wide blade pedal agitator. On the right, we have our original project with pitched pedal agitator. So the configuration on the left has much higher mean drop size, almost by the factor of 2.5, something around this. Now, let's look at turbulence characteristics and let's compare them. The average value of energy dissipation is practically the same, 0.725 versus 0.722. A characteristic time of micromixing is also about the same. However, the maximum value of energy dissipation for this configuration is much higher. I'm sorry, it's much lower. On the right, we have 200, on the left, we have 13. So this increase in maximum value of energy dissipation results in significant decrease of the mean drop size. Therefore, VisiMix gives us an opportunity to compare two different configurations and to find out exactly, to pinpoint, I would say, which particular parameter of turbulence is responsible for increase of mean drop size. Now, let's close this demonstration and let's move on to my main presentation. Right now, we are going to talk about VisiMix, which is a user-friendly, universal, and reliable computational process engineering software for analysis of processes facilitated by mixing. In order to discern important feature of the software, first of all, I'd like to tell you that it supports all tasks routinely encountered by process engineers in their practical work, such as rapid adjustment of input based on output review results, design selection from available alternatives, and so on and so forth. Right now, let's go step by step, and let me demonstrate you, first of all, that it is indeed friendly, universal, and reliable. Here we have the same screen that we just saw in my small demonstration, combined together in a single slide. Basically, we are talking about universal input of mandatory design parameters. Without these parameters, no calculations can be done. First of all, we entered parameters of the tank, of the baffle, impeller type, impeller dimensions, physical properties of continuous and dispersed liquid phases. All of these parameters are universal, and input screens for entering these parameters are also universal. Now, let's move on to the next slide and look at some customized input of additional physical properties necessary for a specific calculation requested by user. On the left, we see the screenshot for input of properties of continuous and in dispersed liquid phases that we just utilized. And on the right, we see properties of solid and liquid phases. And we can see now that there are some differences. On the left, we have some basic properties marked with red arrows. Now, some specific properties for this particular calculation marked with green, and on the right, we have the same universal properties which are identical for whatever calculations we want to do, but the other set of parameters shown with blue arrows is different. The point is that the input is customized for entering additional physical properties necessary for a specific calculation requested by users. So this customization allows user to minimize time necessary for input and demonstrates user friendliness of our software. Let's move to the next slide and let's look at output. First of all, the output is comprehensive and compact. It means that includes all information necessary for engineers to make specific technical decisions without any post-processing, and it is customized to a specific calculation requested by user. On the left, we have nice pictures which show some specific features of flow in the tank. The next screen, we show various hydrodynamic parameters, such as mixing power, Reynolds number for flow, average value of tangential velocity, circulation flow rate. Let's jump through a couple of lines and move to the bottom to the vortex depth. So these are major main fluid dynamics characteristics that would be shown in the main output menu. Right now, let's take a look at another couple of plots. First of all, this is kinetics of draw breakup, which I showed in my demonstration. But if we want something more specific, we have here a tracer concentration in chosen point for continuous flow reactor. So basically, the point is for all of these requests, all output data will be presented in concise and convenient form. But what is even more important, all output data are comprehensive. You will have everything that you need. With this said, let's move to the next slide and talk about the next feature of our software, which is its universality. So basically, first of all, we cover a wide range of design configurations. Let's look, for example, at situation where we're interested in a jacketed tank and how we enter parameters for the jacketed tank. At the first screen, we enter general heat transfer data for the tank. As the second screenshot, we show you the screen for entering tank shell characteristics, such as material, wall thickness, and so on and so forth. After we enter tank shell characteristics, we move to the next, which is heating and cooling liquid engine inject. So here we have, suppose we have water, we have to choose the type of the agent, we have to choose inlet temperature, we have to choose flow rate of heat transfer agent in lower jacket. So after all this done, we can move to the next step, and the next step is batch process heat transfer. If we're interested in batch process, for this particular group of parameters, we also have certain input, and now we can move to the next step, which is conventional jacket and its specific characteristics. We enter width, we enter wall thickness, and we're done basically with this screen. We can move on to heat transfer properties of the media. And basically, this is 6 screens cover the entire design variety of design configurations which are of interest to our users. With this said, let's move to the next screen and talk about universality in terms of process types and characteristics covered. So here on the left, we show the screens that are already familiar to you from the first part of my demonstration. Design configuration and tank sizes are pretty universal. Practically anything you wish is here. But now we're moving to physical processes, and here we have a wide range of them. Let's begin with hydrodynamics, then turbulence, then single-phase liquid mixing, continuous flow dynamics. We have a very wide choice of questions to request, for questions to submit and analysis to request. We have liquid-solid mixing, liquid-liquid mixing. We'll talk about it a little bit in more details, but let's move on. We can choose gas dispersion, mass transfer. Finally, we can choose a bunch of heat transfer parameters. Now, let's assume that we're interested in liquid-liquid mixing, and then we can move on to a list of process characteristics that we can request for this analysis. We can request kinetics of drop breakup. We can request mean drop size. We can request specific mass transfer area. And to say a little bit about each of them, they are, again, they are comprehensive. And finally, we can choose something like distribution of drops by diameter. After all of that, we can conclude that Physimix is universal in terms of types of physical processes and process characteristics covered by our software. Now we are going to talk about even more interesting aspects of Physimix universality. This is universality of engineering tasks that could be performed using Physimix. And we are talking about two very useful tools. The first of them is a scale-up, scale-down tool, which could be found in the ribbon. And right here, it's circled with a red circle, is the button that will allow you to use this very powerful tool. This tool is powerful and efficient for extrapolating a process which has been successfully designed and verified at one scale to another scale. In order to design industrial equipment for a process which has been verified at laboratory scale, select a smaller tank for laboratory research of a new or modified process for subsequent implementation at a larger industrial scale, or fine-tune or adjust operating parameters of previously designed process equipment. All of these important tasks can be accomplished using this tool. Let's look a little bit at the uniqueness of the tool. This tool is unique because it allows user to select a similarity parameter for scale up or scale down. And it could be done using two different options. Number one, we can choose a similarity variable, such as macro mixing time or micro mixing time. Or if we're not sure which similarity variable we are interested in, we can use key process characteristic, such as mean drop size for liquid-liquid mixing. And the system will automatically do the hard job. As soon as Physimix knows which similarity variable or which key process characteristics we want to reproduce in the target tank, it will query our proprietary knowledge base. This is the first time I mentioned our knowledge base, but we will talk about it later on. Then it displays the complete set of target tank design parameters and process characteristics, creating a new project for the target mixing tank. So with this said, let's move to the next step and take a look at the exact choice which we have here. In the red frame at the top, we have a list of scale up, scale down similarity variables. We can choose any of them. And if we're not sure, we can go to the second screen and choose key process characteristics. Now, if we're interested in scale up, scale down similarity variables, we can choose such things as maximum shear rate or mixing time and be happy with this choice. But if we don't know which similarity variable we want to choose, let's go back to the second menu, and we have here very wide choice between complete emulsifying or gas pickup, for example, or several other options. So let's now move to the next slide and look at the second tool that I'm going to show you, which is process analysis tool. Here is the place of this button in the ribbon. This tool supports comparative analysis of several projects for such important tasks as selecting mixing equipment that matches specific process requirements, checking if it is possible to reproduce conditions of an industrial scale process inside an available pilot or laboratory unit, analyzing effects of design and operation parameters and physical processes of mixed materials, or certifying equipment for various production processes. Finally, we can generate reports using this tool. Let's see how it works. First of all, we have select several projects for comparison. Here we see 3 projects. One is with pitch pedal agitator with white pedals. We have the second design, which is hydrofoil, a 2-stage impeller, and here we have glass-lined impeller as a third option. Now we have to choose a process that we are going to conduct. Basically, it is also uniqueness of this tool that we compare different projects specifically for the selected process that we are going to conduct. In this slide, we see that we choose solid liquid mass transfer, but let's move on to the next slide and see what do we have here. So again, as I said, this software allows user to select a process conducted in mixing tanks represented by different projects. Then Visimix will do the hard job by querying our proprietary knowledge base for selecting parameters which govern such a comparison for the particular process selected by the user, and displaying these parameters in a compact and clear table. How it looks. Here is the final output table for these 3 projects. Let's begin thinking about the result. First of all, design number 2 doesn't work because it's, I'm sorry, I forgot to tell you that we are indeed looking for emulsifying all oil-water system and liquid extractors. So the second design doesn't fit the bill because we do not have complete emulsification. Okay, let's move on to the first design. It gives us complete emulsification and the mean drop size of about 1000 microns. And the third design gives us the mean drop size of about 700 microns. So the final choice is yours, but Visimix gives you all information necessary to make the final choice and to finalize your design solution. Now, Visimix is not only user-friendly and reliable and outfitted with very powerful tools for specific engineering tasks. The most important thing is that Visimix is reliable. It is not only user-friendly and universal. The point is that our models are applicable only to cases with reasonably good mixing. The cases with bad mixing are unpredictable. Luckily, they are of little practical interest to user. So Visimix has inherently safer design features which operate in the background. Specifically, input is processed using internal controls, helpful hints, and warnings that prevent users from attempting to enter input data, leading to unpredictable output. Calculation algorithms include many restrictions and warnings that prevent users from inadvertently shifting production process away from its nominal course. So this combination of protective measures implements the concept of inherently safe design and prevent many common mistakes in design process. In absence of such restrictions, even nicely presented output would have no resemblance to real life. And I'm proud to share with you that in 25 years of commercial use by numerous users worldwide, we have never heard any complaints about erroneous predictions that contradict real-life experimental data. In other words, if you ever have prediction by Visimix, you can be sure that in real life, your real measurement will demonstrate something very close to our predictions. Now, let's talk a little bit about Visimix algorithms. So the whole calculation starts with tank geometry, agitator or rotor speed, fluid viscosity or rheology as input data. Then Visimix calculates certain fluid dynamics characteristics. We'll talk about a little bit later. We will talk about specific features of our fluid dynamics analysis. After obtaining fluid velocity, pressure, and turbulence characteristics, we use them as input for process analysis. But on the top of that, for process analysis, we use another input, which is process type and detailed description, customized for a specific calculation requested by user. So in the course of all calculations, when Visimix conducts process analysis, it repeatedly queries Visimix knowledge base. Visimix knowledge base is invisible to user, but it is an extremely important part of our software. It is queried repeatedly in course of input and simulations by individual software subroutines driven by Visimix proprietary algorithms. It encompasses a set of mathematical models of underlying physical phenomena. It is streamlined for obtaining requested output rapidly, for supporting process design based on input-output review and other input iterative cycles, and it allows user to rapidly check various design options, and therefore it facilitates consequent analysis of equipment operation. All of these wonderful features are supported by our Visimix knowledge base, and the iterative querying of the Visimix knowledge base is basically the heart of Visimix algorithm. Let's move to the next slide and talk about Visimix simulation and output. Visimix simulations comprises two steps. As the first step, the process vessel is divided into several large zones. And at this step, we obtain mean values of fluid dynamics variables for each zone by deriving consultant proprietary equations of mass, momentum, or heat transfer, and generation, dissipation, and transfer of turbulent energy for all zones. As the second step, using fluid mechanical properties obtained as the first step as input, we calculate process characteristics of interest for user by using fluid dynamics variables as an input and applying well-verified proprietary mathematical models in order to obtain end process characteristics that are of interest to user. So important to state here that Visimix output provides user with all necessary process characteristics and does not require further post-processing. And this feature is the a sign that our Visimix software is indeed computational process engineering software. So we define computational process engineering as a technical discipline developed for predictive simulations with emphasis on process characteristics, which process engineers are really interested in, such as for single-phase liquid system, it is macro mixing and micro mixing times. For liquid-liquid systems, it is such things as complete emulsification check, drop diameter versus time dynamics, mean or Soter drop diameter, or some other parameters. For liquid solid system with dissolution of solid particles, this is time of complete dissolution or concentration of dissolved solid particles, or dissolved solid or particle diameter versus time. For gas liquid systems, these are such things as complete dispersion check, gas holdup, average bubble number, and gas mass transfer rate, gas pickup from the surface, or volumetric mass transfer coefficient, K sub LA. So this, in our understanding, is computational process engineering. Let's move to the next slide and talk about CFD. We understand CFD as computational fluid dynamics. All of us understand it in the same fashion. So computational fluid dynamics is a method for fluid dynamics analysis. We would like to remind you that fluid dynamics is not the end goal of our analysis. It is always a method for obtaining input for process analysis, which is the most important part of the story. So CFD is a technical discipline developed for predictive simulations of fluid dynamics variables, such as pressure, velocity, flow rate, and turbulence characteristics for turbulent flows. It is implemented today routinely as numerical solution on a three-dimensional fine mesh of hydrodynamic heat transfer mass transfer equations with boundary conditions set on surfaces of complex shapes consisting of both fixed and moving parts. It serves real needs of many industries, and it is popular there because engineers working for these industries really like it. CFD is software for process industries, such as chemical, petrochemical, pharmaceutical, and so on. Evolved from traditional generic CFD packages, it requires significant user skills and resources. It leaves process characteristic simulations to user discretion, or at best, reduces them to empirical correlations between various non-dimensional criteria that are applicable to a narrow range of conditions. Every step of design process requires adaptation of a 3D mesh that dramatically restricts the ability of process engineers to pursue optimal selection of design for obtaining desired process characteristics. Here is the problem with CFD. Process engineers value fluid dynamics variables to the extent that they support subsequent accurate simulation of process characteristics. Today, solving CFD equations is a routine, although cumbersome task. Converting fluid dynamics variables into process parameters is challenging. CFD is like a street line which directs light to a place where there is no wallet. The wallet in this case is correct calculation of process characteristics. And the guy who is a user of CFD, he basically looks for his wallet somewhere where it doesn't exist. So this is a typical street light effect. And a typical question asked in this case, I'm stirring my coffee well, why it is still not sweet? It is still not sweet because we need a better approach. And here is the approach that we offer. Process engineers wish to create favorable conditions in the bulk of the tank and to avoid unfavorable conditions everywhere in the tank. Neither of these tasks requires knowledge of a large number of fluid dynamics variables on a fine mesh. Both can be accomplished based on deep knowledge of underlying physical phenomena integrated in our proprietary knowledge base, which is a set of sophisticated mathematical models preferable to empirical correlations applicable to very narrow ranges of parameters. And right now, I'm going to talk in details about knowledge base. VisiMix knowledge base comprises dozens of models which utilize less detailed than in CFD, but still relevant flow structure for calculating process characteristics averaged over strategically selected large-scale areas of a process vessel. It is verified with well-verified results of long-standing experiments for a broad range of equipment types, design parameters, and fluid physical properties. It incorporates vast practical experience in design and operation of industrial mixing equipment. And it constitutes the heart and the jewel of VisiMix technology. And here is VisiMix approach. So VisiMix is developed by process engineers who pondered long and hard over how to focus on real problems that challenge their fellow engineers. And here is our solution. The guy should stand up, should take a flashlight in his hand. In this case, VisiMix is a flashlight, and direct it to the point where the wallet or process characteristics are located. And Eureka, we avoided completely the street light effect. So my conclusion from this is that VisiMix is the unique computational process engineering software commercially available today for analysis of processes facilitated by mixing. Advantages of VisiMix are shown here. VisiMix is not another garden variety TFD package. VisiMix is a sophisticated process design and simulation software fully adapted to actual needs of process engineers. It is superior to modern CFD packages in terms of lightness of its input, thoroughness of its output, and versatility in supporting process design, which is always iterative. VisiMix is not focused on flow details. VisiMix is focused on reliable calculations of critical process characteristics. And now let me conclude that VisiMix is a truly computational chemical engineering software, which represents a fundamentally new process-oriented approach to simulation, scale-up, scale-down, and analysis of processes facilitated by mixing. VisiMix is a superior desktop assistant for those process engineers who are inspired to improve their expertise in designing, simulating, implementing, and improving various processes conducted in mixing time. With this said, let me complete my presentation and stop share screen. Now, let me remind to you that VisiMix Turbulent, which I showed to you, is just one product in our suite. We have many more of them. So, therefore, please stay tuned for future updates and have a nice day. Bye now.